What if I told you that adding up the squares of all natural numbers reciprocals gives you a beautiful connection to pi? Today, we're diving into one of mathematics' most elegant puzzles, the Basel problem. A problem so challenging that it stumped the greatest mathematicians for nearly a century until one genius cracked it with a solution so brilliant it's still celebrated today. Let's explore this mathematical masterpiece. The Basel problem asks a deceptively simple question. What is the exact value of this infinite sum? 1 plus 1 fourth plus 1 ninth plus 1 16th plus 1 25th plus continuing forever. Or, written mathematically, the sum from n equals 1 to infinity of 1 over n squared. Now you might be thinking, why should we care about adding up these fractions? Well, let's see what makes this so fascinating. If we add the first few terms, we get approximately 1.463. Add 100 terms, about 1.635. 1,000 terms, around 1.644. The sum clearly grows, but very slowly. It appears to be approaching some finite number. But what number exactly? This question emerged in the mathematical community around 1650, originating from the Italian mathematician Pietro Mengoli. But it became famous thanks to the Bernoulli family in Basel, Switzerland, hence the name Basel problem. For nearly 90 years, this problem taunted Europe's finest mathematical minds. Pietro Mengoli posed it, but couldn't solve it. The Bernoulli brothers, Jakob and Johann, titans of 17th century mathematics, attacked it relentlessly, but failed to find the exact answer. Jacob Bernoulli managed to prove that the sum converges, meaning it doesn't go to infinity and that it's less than 2. He could calculate it numerically to several decimal places, but the exact value? It eluded him completely. On his deathbed in 1705, he still hadn't solved it. Other brilliant mathematicians tried and failed. Stirling, de Moivre, even the prodigious Euler initially struggled with it. The problem became one of the most famous unsolved questions in mathematics. It was the mathematical equivalent of climbing Everest. Then in 1734, a 28-year-old Leonhard Euler accomplished what seemed impossible. Leonhard Euler was already making waves in mathematics, but his solution to the Basel problem catapulted him to fame. And his approach? Absolutely ingenious. Euler started with something familiar, the sine function. Now stick with me here, because this gets beautiful. He knew that sine of x equals 0 at x equals 0, pi, 2 pi, 3 pi, and so on. These are the roots of the sine function. Euler had a wild idea. What if we treat the sine function like an infinite polynomial? Just as a polynomial can be factored using its roots, Euler wrote sine as an infinite product. He started with the Taylor series. Sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Dividing both sides by x gives us sine of x divided by x equals 1 minus x squared over 6 plus x to the 4th over 120, and the pattern continues. But as an infinite product with roots at plus and minus pi, plus and minus 2 pi, and so on, he wrote it as 1 minus x squared over pi squared times 1 minus x squared over 4 pi squared times 1 minus x squared over 9 pi squared, and so on, continuing infinitely. Now here's the magic. These two expressions for sine of x over x must be equal. If we expand the infinite product and compare the coefficient of x squared on both sides, something extraordinary happens. From the Taylor series, the coefficient of x squared is negative 1 over 6. From the product expansion, when we multiply out all those terms and collect the x squared terms, we get negative 1 over pi squared times the sum of 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, and so on. That's exactly our Basel sum, setting them equal. Negative 1 over 6 equals negative 1 over pi squared times our Basel sum. Multiply both sides by negative pi squared, and solving for the sum gives us the answer. Pi squared over 6. The answer to the Basel problem is pi squared divided by 6, which equals approximately 1.64 4934. An infinite sum of simple fractions equals exactly pi squared over 6. Who would have guessed that pi, the ratio of a circle's circumference to its diameter, would appear here? It's one of mathematics' most unexpected and beautiful connections. Euler's solution was revolutionary, but we should note his methods weren't rigorous by modern standards. He treated infinite series like finite polynomials without complete justification. But he was right. Later mathematicians, including Cauchy and Weierstrass, provided the rigorous foundations Euler's brilliant intuition deserved. This wasn't just an intellectual victory. The Basel problem opened doors to an entire field, the study of zeta functions. The Riemann zeta function, which generalizes this problem, is central to number theory and connects to the distribution of prime numbers. The famous Riemann hypothesis, one of the million-dollar Millennium Prize problems, is built on these foundations. And Euler didn't stop there. He found that the sum of 1 over n to the fourth equals pi to the fourth over 90, for n to the sixth, pi to the sixth over 945. He discovered a whole family of beautiful formulas. The Basel problem teaches us something profound about mathematics. Sometimes the most elegant truths hide behind simple questions. A sum of fractions that any student can understand connects to the geometry of circles through pi, revealing the deep unity underlying all mathematics. So next time you see pi, remember it's not just about circles. It's woven into the fabric of numbers themselves, appearing in places we'd never expect. That's the beauty of mathematics: infinite mysteries, elegant solutions, and connections that take your breath away. If you enjoyed diving into this mathematical mystery, hit that like button and subscribe for more mind-bending math content. Drop a comment telling me which famous math problem you'd like to see next. Until then, keep questioning, keep exploring, and remember, in mathematics, the impossible is just an unsolved problem waiting for its Euler.